Okay, so we're gonna get started here. Are people okay with the lights dim like this? I much prefer this to the flashing lights over there, so uh, stick with this unless there's a critical mass to do otherwise. Um, Alright, so while the last people trickle in, so we're on lecture 3 today. This will be continuing the linear regression that we were discussing in the last lecture. So just one quick logistical announcement. So the practice quiz, so the first of the weekly quizzes will go out this week. These are called Quiz 0 because we're still in the add drop period, so this does not actually count towards your final grade. So again, as the same is going to be the same procedure as it will be in all other weeks, but in those weeks, your best quiz for the week will actually count towards your grade. So this is for practice for you, these quizzes, in order for you to get a sense of where you're at with respect to the prerequisites for this course. So these quizzes should be doable just based on knowledge you have from previous courses. They involve things from probability, from calculus, etc. And if you're really struggling with these quizzes, this is maybe a signal that for some of the more mathematical background, it might be a little difficult and maybe worthwhile knowing that you're going to put extra work in, or that you might want to postpone to a later semester if you're still an early undergrad. And also, in addition to being practice for you, they're also somewhat for debugging. So if there's any major issues, please bring things up on the discussion board. They should be open for 1 hour when you start them, and you won't see the answers. You'll see your grade at the end. But then once the quiz is finished, so for quiz 0, attempt 1, on Wednesday at midnight, the answers will show up. So you will get feedback on what you got wrong, but just not immediately, because then people could team up and just share answers, which we want to avoid. Okay. Is there any questions on the quizzes, on logistics? Okay, and otherwise, the other logistical thing is that the first mini project will ideally be out by end of day Thursday. It's a bit tricky with add drop period. People are still coming in and going, so I know making teams can be a little bit tough. But I want to get you the material for that project as soon as possible. So if you're already have a team and want to get started, you can get started. And again, this mini project, the first one, is going to be a little bit lighter than the later two. So you'll have plenty of time to finish it before the deadline. Okay, so with that, moving into the actual content. So today we're returning to linear regression. So just as a quick recap, linear regression is this challenge of trying to find a linear function that best fits some given data. So in particular, we have some targets y that we're trying to predict based on some input features or variables x, and we want to find the best linear function so that the square difference between our predictions and our targets is small. So we're trying to minimize this squared loss. And we did a little bit of math, a little bit of vector calculus, and came up with the least squares solution. So here I'm showing this closed form solution. This is this kind of fundamental equation in machine learning and statistics, where to get the prediction or the predicted weights, or our best fit weights for a linear model, we're computing this by taking our data matrix. So this is X is our matrix that has each of these rows in X is going to be a different data example, and each of the columns is a different feature. So we're taking X transpose X, taking the inverse of this, times X transpose Y. Now, of course, we also discussed some other ways of solving this using gradient descent. That's actually what you're going to do in your mini project. But for now, we're going to focus a little bit on this closed form solution, because it's going to help us kind of tease apart some of the failure modes for linear regression. And that's what's going to be the focus for the first part of today's lecture. So supposing that we have a reasonably small data set, and we can solve this problem, you'd think pretty easily just using, say, MATLAB or using NumPy in Python. That's what I'll recommend you use. But the question is this always going to work well? So is taking our features, our information that we have, putting it through this particular equation, is that always going to give us a good estimate? Is it always going to actually make good predictions or even work at all? And as you might expect, it's not always going to work. Sadly, simple linear regression doesn't solve every problem in machine learning, and there's really two main failure modes. So the first failure mode is really when the model completely falls flat on its face, and when it doesn't even really work. And that is this case when this matrix X transpose X, when that matrix is singular. So remembering from linear algebra, if this matrix is singular, if it has some 0 eigenvalues, its inverse is going to be undefined. So if this inverse is undefined, well, then we can't even solve this equation. So there's no way for us to get anything off the ground. So this is a very catastrophic failure mode. The other failure mode is just when the model doesn't work that well, just when our predictions are terrible. Now, there's a variety of reasons why our prediction could be terrible, but the most straightforward reason for this is that the data we're trying to predict is not actually linear. So we're assuming that a linear model is going to fit our data well, that we'll be able to predict our targets, our outputs, as a linear function of our input features, but a lot of things in the world aren't linear. So for example, in the bottom right here of this slide, I'm showing a function where we might just try to fit here, how can we predict the recurrence time of a tumor, that's the y-axis, from the radius of a tumor, that's the x-axis. And when you look at this, you can see we've plotted the best fit linear line. It doesn't really look like it's fitting much. So it's really hard to say that there's really any linear signal in this tumor data set. So this is the other failure mode, is when we're trying to use linear regression, it's just predicting terribly, and that's because in reality, the function we're trying to fit, or the true underlying relationship between our input features and our target, is actually not linear. Any questions at this point? Cool. So going into a bit more detail into these two failure modes. So the first failure mode, again, comes from this case when this X transpose X matrix is singular. And what this means for this matrix to be singular is that it doesn't have full column rank in the formal terminology of linear algebra, but the best way for you to think about this is that it means that there's correlation between the features. So in particular, if we have a singular matrix here, this means that one of our features can always be predicted from all of our other features. Yeah? Yes and no. So it will work, but the guarantees I talked about in the last lecture don't hold. Because basically there isn't a unique solution anymore. So it's an important caveat for the guarantees I mentioned is we're assuming that these matrices are not singular. But for your matrix to truly be singular, it has to be a pretty bad. What that means is that you essentially have two features that are perfectly correlated with each other. It means you've kind of replicated some information unnecessarily. So as an exercise, you might want to think about, not going to ask you to do it on the fly right now, but again as a thing to do after the lecture when you're reviewing is, when does this happen? You can think about kind of practically when might you end up with features that are totally correlated, what sorts of coding errors could lead to that, and then try to design an example, try to solve it, see what happens when you plug that into NumPy or into MATLAB, just to get some experience with this. So these difficult cases, they really can be summarized into two different standard situations. One is the situation I was alluding to earlier, and this is where we basically have that one of our features is just a function of the other. So for example, if we have some feature xm that is always just equal to 2 times the feature m minus 1, xm minus 1 plus 2, this isn't giving our model any more information. We're just providing the same feature twice, just a linear transformation of it. And so if this is the case, if our model's breaking because we've done this, and this can happen occasionally, not because you're making a mistake, but maybe you're taking a data set off of some website, or you're scraping data, and there's all kinds of deterministic kind of correlations like this in the world. So this can happen. And what you have to do is you have to just figure out what variables is essentially, or features to delete, or how to code them in some way so that you don't have this strict correlation between them. Now, the other way that this can happen, where you can end up with a singular matrix, is kind of simpler. It's very easy to know when it happens, and that's just when you have more features than you have data points. Now, that's also not going to work. You're going to end up with a singular matrix there, again, quite trivially from linear algebra. If your column dimension is larger than your row dimension, then you can't have full column rank. So, again, what do you have to do if this is the case? If you have way too many features, well, then the simplest thing to do is just reduce the number of features. You can also apply some techniques that are called regularization, which will be the subject in detail of Lecture 6. So the takeaway here is just that if you're running linear regression and it totally breaks down, probably what's happening is one of these two cases. So this is not, the most exciting failure mode, but it's something to watch out for. And again, it's something to watch out for when you start using gradient descent-based models, because they're not going to fall flat on their face so obviously as getting an error from a linear algebra library. But it's important to know that if you're doing things like having way too many features that are all perfectly correlated with each other, your machine learning model is going to have a very bad time. Okay. So now going to move on to the slightly more interesting failure mode. So in this case, this is when our model ran, things seemed to work, but when we look at how well our model's predicting, it's really doing terribly. And right now, when you're just running linear regression and, say, getting mean squared errors, you're not going to exactly know, like, is this a good mean squared error? Is this a bad mean squared error? And this is something you're going to have to develop intuition for, and also something I highly recommend everybody does is make sure you always plot your data. So when you're making predictions, when you're working with data, don't just trust that everything is working fine. Visualize things, look at things, and for example, in this case, if we were to look at how well we are predicting recurrence time from tumor radius, it would be pretty obvious that there's no signal here at all. So what can we do to fix this problem? So one obvious solution is that we could try something other than a linear model, and that's going to be really what a lot of this course is about. We're going to move beyond linear models eventually, but we can actually get nonlinear information while we're still using a linear model. And how we can do this is by adding more features, and that's going to be the focus for most of today's lecture. The other thing that sometimes helps in machine learning, at least it never hurts, is just collecting more data. Maybe if we collected 10 times as much data, we'd end up that it's actually a pretty good signal here, but of course, you don't always have the ability to collect more data. Oftentimes, if you're in a Kaggle competition or you're trying to do something for one of our mini projects, it's not going to be straightforward to just add more data into your model. So today and in the previous lecture, we've always just been talking about this case where we have simple quantitative numerical variables. So we're always assuming that we just have these input variables, x1 to xm, or these input features, and for simplicity, we've just said, okay, these are always just real-valued numerical features. Now, life isn't always that simple, and just using these original quantitative variables isn't always enough, in particular if our model is really not doing well, if we're not getting a good performance at predicting our target. So what can we do? The important thing that we can do is that we can actually take transformations of our input variable that's going to allow us to actually get some kind of more interesting, say, nonlinear information rather than just using what we're given. So, for example, we could take the logarithm, we could do basis expansions, so we could take the square or the cube, etc. of these variables. So we can take really any kind of function you want. Again, you want to be careful that these functions should be interesting nonlinear functions. Otherwise, you're going to end up just having correlated features that are going to break your model. We can also add interaction terms. This is kind of interesting, is that rather than just looking at a variable x1 and x2, so for example, say we have the tumor size and the tumor color. Now we can look at those two different features independently, and our model can use that information, but maybe it's the case that tumors always have a very fast recurrence time if they're large and they're dark. In order to get these these AND relationships, you actually have to add explicitly interaction terms into your model. So what you do is you add a term that would be the kind of cross product or the multiplication. So say these are both just numeric variables, you just take their multiplication. It gets a little bit stranger when you have categorical variables, but you can think that it's basically just taking a cross product. And of course, not all of our variables are going to be simple numerical variables, so you also have to think about how you're encoding the other types of variables you have. So say you have a binary variable. This variable might say, for a tumor, you might have a binary variable that says, is it rough or smooth? So how you'd encode that in the model is maybe you set smooth to 1 and rough to 0. And it doesn't really make sense to use values other than 0 and 1 here, because that's not going to make a difference to the model. But having a standard binary encoding will work. And in all cases, we're just going to take all these new variables we've constructed. So we had our original set. We took the logarithm of a bunch. We took the square and the cube of some of them. We made some interaction terms. And now we can add all these new variables to our model. We don't want to go crazy here, because if we just add everything under the kitchen sink, we're going to end up breaking our model again by having too many features. And features aren't always going to help. Adding more features isn't always going to help, as we'll show in the next few slides. But I'm just going to take a second to highlight that variable coding is not always straightforward. Of course, there's the one difficulty of just choosing, should I add the squared terms? Should I add, maybe a log? And a lot of this is going to come from kind of intuition, depending what kind of data you're using. There's going to be techniques we're going to describe for how to automatically choose what are the right feature transformations, etc. But even in simple or seemingly simple settings, choosing how to encode a variable can be a little tricky. So here I'm showing the example where we have a simple categorical variable. Say we have a variable that can take 4 values. It can be blue, red, green, or yellow, right? So the question is, how are we going to encode this variable? Now, the solution that you might think would be, okay, this is a totally reasonable thing to do, is we can just say, okay, we have 4 separate binary variables. We have one variable that says, is this thing blue or is it not blue? Another one that says, is it red or is it not red? Another one that says, is it green or not green, etc. So we're basically just taking this categorical variable and breaking it up into 4 separate binary variables. Now this is actually going to break your model if you're using a simple linear model, because you're actually introducing some features that are perfectly correlated with each other. So this solution will not work. So what will happen is that if you have 4 of these different variables, well then if we know that this variable is not blue, red, or green, it has to be yellow. So we have this issue where there's this perfect relationship between these different variables we introduced, and that's going to break your model. So the correct thing to do is actually just to have 3 separate binary variables, say for red, green, or yellow, and then you don't have any variable or any feature that has anything to do with the blue value, because we just know that if we don't have a 1 for red or green or yellow, then we must be blue. So in a sense, what's actually happening here is that the blue category is being kind of folded into the intercept term. We talked about this intercept or bias term in the last lecture. So that's what's happening to the blue variable here. And again, if we did solution 1, if we just made 4 separate binary variables, this is actually going to lead to a singularity in our data matrix. And you can think about crazier ways to try to encode this. This is a standard way. Solution 2 is called dummy encoding. But there's all kinds of other things you could do if you wanted to get creative for kind of extract more interesting features from this categorical variable. And things are also not always straightforward, because sometimes our data is not numeric, nor is it categorical, nor is it ordinal. It's really something a lot more raw. So for example, we might just have text data or image data. And in these cases, you need to get creative, and we're going to kind of walk you through a very simple example of this in the first mini project. But you need to actually think about, how can I go from text and extract some useful information? Maybe you take word counts. maybe you get the average word length, number of words per sentence, etc. So going from some raw feature information to actual numeric values that you feed into your machine learning model is a huge proportion of the work in machine learning. And we're going to return to this continually throughout the course. But for today, we're going to stick with the simple case where we're mainly just dealing with quantitative variables, and we're going to focus on this idea of adding transformations of these original quantitative variables in order to make our model more powerful. So to give just a quick example of what this actually might look like. So again, here I've returned to this simple little toy example that we started in the previous lecture, where what we're trying to do is we're trying to predict the y value, so the y-axis in this figure, from the x. So we want to have some function that can predict y from x. Last time we went through a whole example of how to solve this in a simple linear regression setting. But now we're going to mix things up, complicate things a little bit by adding in the square of x. So now we don't just have one feature. Now we have two features. We have x and the square of x. And we're going to try to predict the y value as a linear function of these features. Again, it's something to make sure that you keep straight in your head, which is that here we've added in a nonlinear function of x as an input variable. But our function f is still just a linear model. We're still just a linear function of all the input features. It's just some of those input features themselves can be nonlinear functions of things. So we always still call this a linear model. It's just a linear model with polynomial terms. It's an important thing to keep in mind because we're going to discuss nonlinear models later in the course, where the model itself involves nonlinearities. So if we did this, it would be pretty straightforward to solve this model. Now we just have an extra column in our data matrix. We can go through the same computation we did before. So we take our data matrix, take the transpose of that matrix times itself. This gives us the matrix shown here at the bottom of the slide. And then again, we also get the other data matrix that we need, which is x transpose times our output y. We put these things together, we find the inverse. Again, in practice, you're going to find this inverse using some linear algebra software, preferably NumPy in Python. And at the very end, we would end up that the weights we obtain by running all of this is that we get a weight of 0.68 for x squared, 1.74 for x, and 0.73 for our intercept term. And visually, what this is going to look like is the image in the bottom left of the slide. So as you can see, this actually looks like it's fitting things a little bit better, right? If you remember from the last lecture, we had this linear fit down here. That was pretty good, but you can see that, maybe there's a little bit of an upturn in the top right-hand corner of this. It's not entirely clear, but by adding in this extra term, we now have this slightly more complicated polynomial function, whereas last lecture we just had this simple linear order 1 polynomial. So you might be wondering, okay, so things looking pretty good with order 2. Now what happens if we might want to add even more features so we can fit the data even better if we even make our model even more complicated? So for instance, we might want to take the order 3. So this is running that exact same linear model, but now we've added in the x cubed term. So we have an x squared, and an x cubed. And you can see that actually this might look even a little bit better than the x squared because it didn't really make sense that in this x squared one we have this kind of it jumping up towards, kind of going back up as we go towards the bottom left. So this order 3 fit, it's maybe looking like it's matching the data a bit more, even more perfectly than the order 2. And you might say, well, what about order 4? And things start to get, it's a little funky. And then we get to order 5, things get even funkier. And we can continue doing this up to order 6, order 7, not much is changing now, order 8, order 9, and now obviously we've got issues here. So what's happening now that we've actually gone all the way up to order 9, we have so much degrees of freedom, we have so many features that we're actually perfectly fitting every single one of these training points. So that's great, right? Like we're perfectly fitting every single one of these training points, but the function's crazy. I don't think any of us would expect that this function would actually predict well on a new data point in this data set. So say we held one data point out, and then we tried to predict on this unseen data point, it's going to do pretty bad. And in fact, we probably would have been better sticking maybe even back with order 1 or order 2. Now this is called overfitting. And this is one of the most fundamental concepts in machine learning, and day-to-day machine learning research is all about trying to make your model not overfit. What does overfitting mean? Well, overfitting means that we can find a hypothesis that can perfectly explain all of our training data. But it might not be the case that this hypothesis, that this model actually generalizes well to new data, to data we haven't seen before, or data we haven't trained. So in this previous example, like I said, our model had enough information, had enough features that we were perfectly fitting every single point that we're training on. But this model's crazy. We know that if we put some new point into this prediction, it's going to be way off the map. And why this happens is because we have way too many parameters, we have way too many features, so the model's matching all of the training points exactly, but it's just wild everywhere else. And this is a very important, like I said, a very fundamental problem in machine learning. So a bit more formally, what's going on here is that in reality, every hypothesis, every model that we build in machine learning has some true error, right? It actually is some true error. It has a particular performance at being able to predict on the task we care about. So if we're building a spam classifier, this model might have an 85% accuracy if we were to run it on every single email in the world. If we could measure it on all possible data items, or if we're trying to predict tumor recurrence, our model might have a particular accuracy if we were to measure it on every single possible tumor data set ever in the world. But unfortunately, we're never actually going to measure a model's error on every single data point that ever could possibly be evaluated on. And this is the issue where what we actually have access to is just a training set. All we know is how well the model's performing on some sample of data, and we need some way to know that this model is actually generalizing to new data sets or unseen data well. And then formally, if we're going to kind of formalize this notion of overfitting, what we're saying is that if we have some function or hypothesis F1 that has lower error on the training set, but if it in fact is worse than F2 on its true error, so how well it would perform if we ran it on everything in the world, then this would be overfitting. And this notion of overfitting is closely connected with one of the other really core central concepts in machine learning, and that is generalization. So in machine learning, our goal is to develop models that generalize. Our goal isn't to just fit some particular data set that people give us. Our goal is to build models that actually work. So again, for spam classification, if someone gave you a data set of here's some spam emails, here's some non-spam emails, and you came back and you said, look, I can predict every one of these 100% accuracy, that doesn't matter. All that matters is that if they actually took your model and deployed it in production, what accuracy is it going to get? So how well is your model actually generalizing? And again, with tons of parameters, with a little bit of effort, it's really easy to overfit your training set. In fact, one of the things that I often tell, especially new researchers to machine learning, is one of the best ways to debug if your machine learning model is actually working reasonably well, especially for more complicated models, is that you should be able to overfit, get 100% on your training data. Once you can do that, you're like, okay, there's no bugs in my code. And then you go on to actually building a model that can generalize. So fitting the training data is the easy part. That's equivalent to just debugging. Having a model that can generalize, that's the real challenge in machine learning. But again, the issue here is that we have to actually have some way to evaluate generalization. We don't get access to the production environment. So we have to have some way to estimate our generalization performance using only a sample of data. Any questions at this point? Okay, so returning to our previous example here, we want to estimate which of these hypotheses, where the first row is looking, pretty reasonable, the bottom row looking a little crazy. Our goal is to figure out which one of these hypotheses has the lowest true error. And just as a refresher, I go back and forth between saying hypothesis and model. That's again just coming from my stats and my machine learning background. So generally stats people say hypothesis more often than model, whereas model is more common in machine learning. But I'll switch back and forth between the two. Now, what many of you may have guessed in terms of how we're actually going to evaluate the true performance of our model is that we're going to hold out data ourselves. So, like I said, what we really want to know is that how well would our model perform on data it's never seen before? How well will our model perform, once we deploy it in a production environment, or when we collect a new set of tumor recurrence data? We want to know how well is it going to do in the future, or on things we've never seen before. Now, in an ideal world, what we'd all do is that we'd build our machine learning models and we'd wait for more data to become available, and then we'd test them without changing anything. But unfortunately, that doesn't really fit with the fact that we have to make things work a bit faster than that, and sometimes, again, we only have access to some particular public data set. So what we're going to do is we're just going to hold out some information from the model. We're going to partition the data, the sample of data that we have. We're going to partition that in such a way so that we're going to only train the model on one portion. We're going to call this portion the training set. And then we're going to validate the model, figure out, what are the features we should use, what do we think the true performance of this model is. And then we're also going to have this data set that we call the test set. So this is an extremely fundamental thing because, a lot of the most embarrassing mistakes early on in machine learning is thinking that your model is performing extremely well, and that's just because you're evaluating on the training set. Or more often it's because you accidentally have some overlap between your training set and your validation set or your test set. And so these are the three chunks of your data. Usually your training set is going to be the biggest chunk. Obviously you want to use a lot of information to try to fit your model, so you're trying to learn the parameters. You want to have as much information as you can in that portion of the data set. But you need to leave enough held out so that you can use your validation set to figure out, what kind of model you need. So when you're trying to decide, should I include squared features? Should I include, maybe I want to do some logarithmic features. Maybe I want to try some different encodings of these text features. You're going to use your validation set to figure out, okay, this looks like this model is performing the best. And now you've tested 50 of them, and you said, okay, on my validation set, this held out proportion of the data, I can see that my model is doing reasonably well. And then the test set is what you're actually reporting the final accuracy on. So this is important, the split between the train set and the test set, the validation set and the test set, because the test set's going to be the thing where if you're writing a paper or if you're going to, somebody who's running a company and you're saying, like, look how well my model performs, that should be your performance on a data set that you've only ran on once, ideally. Of course, in the real world, test sets get run on more than once. There's lots of public data sets with public train validation test splits. But again, if you're having proper, what we might call proper machine learning hygiene, you should only be running your final model, the model you think is the best model you have. You say, okay, now I've got this. Now I'm going to run that on the test set. So just to break this down in terms of an example and in terms of proportions that are reasonable. I mean, this is a tiny data set, but we're again looking at this same little simple data set that we talked about throughout the course. And so here, what we're going to do is we're going to take about say 2/3 of this data. We're going to use that to train on. We're going to call that the training set. We're then going to have this validation set. And then we're going to also have a couple data points held out for our test set. Now, it's important to kind of drive home this difference between this validation set and this test set. So your validation set is used to compare different models while you're developing. So what might this mean? Well, there's two important versions of this. So one is comparing different hypothesis or model classes. So what this means is that you might be choosing between a linear model with certain set of features or a linear model with other features. Maybe you want to use something let's call a neural network or some decision trees that we'll cover later on in the course. You're going to use this validation set to compare these different options that you're looking at. And the other important thing you're going to use this validation set for is to compare what are called different hyperparameters. So hyperparameters, really important terminology. These are parameters that is not learned by your model, but that could impact performance. So we've been talking about the parameters of a linear model. So just to give a concrete refresher, the parameters of a linear model, they are these numbers that we're learning here. So we learned that there is a weight of 0.68 on the x squared value, there's a weight of 1.74 on the x value, and there's a bias term of 0.73. These are the learned parameters of our model. But oftentimes there's aspects of our model that aren't learned. And in particular, what we talked about in the last lecture was this learning rate. So this learning rate is an important parameter. Like we said, you have to set that learning rate right if you want your model to work. And when you start working with more complicated models that aren't linear regression, your performance is going to depend on your learning rate. Your performance is also going to depend on various other aspects of what type of optimizer you're using in a library. We'll cover that later on in the deep learning portion of the course. But it's important to know that we always call all of these things, all of these decisions that we're making that impact our model, but that aren't actually part of the learned model, we call all those things hyperparameters. And so the other important thing we're using the validation set to set is these hyperparameters for our model. And the test set is, again, just used to evaluate the final performance. After we've chosen our model, after we've chosen our hyperparameters, now we're going to use the test set to actually evaluate the final performance and tell how well we're doing. And so you might ask, well, why is it so necessary to separate these things? And maybe this is obvious at this point because I've really been going on this point, but it's really important. So why do we want to separate them? Well, in fact, because what can happen is that if you don't separate your validation set and your test set, you can end up with what we call a form of meta-overfitting. So overfitting was this issue where your model is too complicated for your data. So what this means is that your model kind of has too much degrees of freedom so that it's predicting all of the training points perfectly, but it's not doing well in unseen data. Well, if you're not careful and you try too many things when you're validating your model with your validation set, you can end up indirectly overfitting to your validation set. So what this means is that even though you're only ever just training your model in your train set, testing on the validation set, and you're saying, okay, well, it does better when I have log features or when I have squared features. And if you try a million things to get better and better on your validation set, you're actually going to start overfitting, and there's not really any real signal there. It's now just randomly you happen to find some model that did a bit better on the validation set, but it's not actually doing better on the test set. So it's important to separate these things, because if we didn't do this, people would end up overfitting accidentally, and people do this all the time, and it's kind of something that's very hard psychologically to avoid. But people would end up overfitting to the test sets, and we'd say, look, we can predict tumor recurrence, or we can predict lung cancer from chest x-rays with 95% accuracy. But then when we actually give it to doctors and doctors start trying it on different sorts of data sets, it completely falls flat on its face. That happens even when we have this separation of train and validation data, because whoever was building these models was spending way too much time working on these validation sets. And this has happened many times within machine learning. So there are many famous data sets where we've overfit to just the test sets on these data sets. So there's examples where, even humans, it's not possible to get correct on everything, but our machine learning models can for, say, object recognition tasks. And the only reason this is possible, why we have models that perform better than should be even possible, is because over the last 5 years, as a community, we've overfit to these data sets. And this is part of the reason why in competitions, so I've mentioned this Kaggle competitions a couple times, and I suppose that now I'll just take a second to explain what that is. So Kaggle is a company that hosts machine learning competitions. In this course, in mini projects 2 and 3, you're actually going to compete in a local competition. It's not going to be with everybody in the world, it's going to be with people in this class. But Kaggle and other companies that host machine learning competitions, they actually hold out a test set that nobody gets to see. And more than that, you only get to submit one model, say, per day in order to get scored on that test set. So there's these strict restrictions in these formal machine learning competitions where it actually prevents you from cheating both on purpose or accidentally. Because again, you could think that if they had a hidden test set, but then they gave you the answer for how good your model did on that test set every time you sent in a model, you could just try 1 million random models, and one of those is going to happen to do well on that hidden test set. So this is extremely important, and this is something to watch out for whenever you're building models, whenever you're reading papers. You have to have in mind, am I having good data discipline? Am I overfitting to my validation set? It might make you feel good at the time. You're like, look how good my model's doing. But at the end of the day, you're going to be disappointed when you actually run it on the test set. Or if you get really sloppy and you say, okay, I think my model's ready, I'm going to run it on the test set. And then like, oh, okay, no, I can do better. I can do better than that. And then you run again on the test set. And you're like, well, okay. And then a week later, you're like, you know what? I wasn't in a good space there. I wasn't building good models. I'm going to try it again. And then next thing you know, 4 months later, you've actually tried like 60 models on the test set. You're just kind of cheating both, I say, like cheating yourself, but also it's unfortunate for the community because these kind of things lead to situations where people publish new crazy high accuracies on, say, public data sets, but that there really isn't a better model there. So we're going to strictly enforce best practices for this splitting, and this is going to be something that's going to happen for all of your projects, including the final project. Now, one thing you might be wondering is you're like, okay, well, this is a bit rough. Like, I have to do all this data discipline. How do I know when I'm overfitting too much to my validation set? Like, I want to try a bunch of models, but now I'm just going to end up overfitting, and all is lost. So that's kind of the case. You definitely don't want to go crazy trying out a million different models on a validation set. But one of the things you can do is that you don't need to just have one validation set. You can actually do what's called cross-validation, and you can end up having many, many validation sets, and that lets you get better estimates of how well your model's actually doing and allows you to try more things and explore more without running this risk of overfitting to your validation data. And I should say that what I'm talking about here is really for the validation portion. There should always still be a held-out test set that you've never ran your model on and that you only run at the very end. Again, this is a very strict, you won't see every machine learning paper following these rules, but they're rules everybody should follow. So this idea with k-fold cross-validation, this idea is that, well, if we want to just get an estimate of generalization, why do we just choose one validation set? Why don't we choose one chunk of our data, use that as a validation set on, experiment 1, then in experiment 2, let's use a different chunk of our data, and so on and so forth. So we call each of these different experiments a fold, and this is nice because now we have, instead of just one validation set, we have k validation sets. Any questions at this point? Yeah. It's a good question. So the question is, once you overfit, is there a way back? And so I think you're probably referring to, I guess there's 2 versions of overfitting that I've been alluding to. So one is the simple version where you're just overfitting to your training set. And yes, there's lots of ways to go back once you're overfitting there. And in particular, you need to simplify your model is one solution. So maybe you added too many crazy parameters, and now your model's not doing well. The other thing you can do to kind of help yourself when you're overfitting on the training set is you can add what's called regularization. And we're going to go into this in detail in, I believe it's lecture 6. It's a whole lecture on this. But regularization is basically the idea that instead of just fitting your model, you fit your model. So you want to say, find me the model that has the lowest mean squared error. But then you also add a penalty term that penalizes complex models. So in the simplest sense, you could say, find me the model that has the lowest error, but then I get a penalty for the number of parameters I have, or the weights of these parameters. So that's an easy way to get out of overfitting on a training set. And generally, regularization, the techniques we'll talk about, almost everybody uses these all the time for any machine learning model. It's very uncommon for your model to not overfit just kind of on its own, especially with more kind of modern deep learning models. So the other form of overfitting, So the other form of overfitting that's more pernicious is when you've kind of accidentally overfit to a validation set. This is a tricky thing to kind of say, like, how do I back out of this? Generally, the only thing you can do is really use this kind of cross-validation. So if you've been using one particular validation set and you're worried that you've been working on that way too much, I'm talking like you spent, like a month just hammering on this validation set, then the only thing you can do is that you can say, okay, I'm going to sample a new validation set. I'm going to kind of mix things up, shuffle things a little bit. But this is why this is risky, because there's really no way to back out of overfitting to like a test set that is a public benchmark test set, because yeah, your model might be overfit and not perform that well, but if that is the standard test set everybody uses, you're kind of polluting it a little bit by having a model that looks like it does really well, but actually isn't a good idea because it's just overfitting. So sadly, there's no real way to remedy kind of like drastically overfitting to a test set in like a public benchmark. Yeah. Yes. So that's the important point of this validation set. So I should say, I mentioned maybe there should be a third point there that I'll add after when I update the slides. So what I said here, this validation set is used to compare different models during development. The important thing you're comparing these different models on is how much they're overfitting. So we usually, and I'll say in a couple slides, we contrast between underfitting and overfitting. But the validation set, this is the thing that's telling you, is my model overfitting? And if you're overfitting to the validation set, you're probably if you're overfitting on the validation set, so you have really low train error, but really high validation error, you're almost certainly also going to be overfitting with respect to the test set. Or if you want to do things in, in some sense, the most effective way, and you do this cross-validation, if you find that your model is, so here you're comparing what is my training error versus my validation error on each of these K folds. If your average training error is way lower than your average validation error, then you're overfitting. And when you're doing this kind of cross-validation, you really don't need to worry as much about this idea of kind of like meta-overfitting that I'm talking about. If you're doing 10-fold cross-validation and you have 1 million data points, the odds of you having the exact same splits even more than once is pretty low. So you can really get a good sense of overfitting just by comparing how well am I doing on the training set versus how well am I doing on the validation set. And in a world where people use cross-validation, how well you're doing on the validation set is a really good indicator of how well you're going to do on the test set. Does that make sense? Yeah. Any questions before I move on? Nope. Cool. So if you take this idea of cross-validation to the extreme, which is really good to do if you have small data sets and efficient compute power, you can do what's called leave one out cross-validation. So if you're trying to get the closest estimate, you're trying to get a validation estimate of how good you think your model is, and you want that estimate to be absolutely the best it could possibly be, well, then you use what's called leave one out cross-validation. And what this is it's this idea of k-fold cross-validation. So every different fold, every different experiment, we're holding out one chunk of the data as our validation set. But in leave one out, these chunks are just one data point. So this means that the number of folds is equal to the number of data points in our data set. So algorithmically, so what would this look like? What we do is we'd repeat n times. So we're going to set aside in our first iteration one particular data instance. We're going to use all other data points to fit our model. We're going to measure the prediction error on this held out data point. And then at the very end, we're going to average how well we did over the whole data set. So this is nice. This gives us a really good estimate. And this is exceedingly hard to overfit to. If you're doing leave one out cross-validation, it's probably really, really unlikely that you're going to start accidentally meta-overfitting to your validation set. But what's the catch here? Well, the catch here is that if you think about the computation, we've added a whole order n, where n is the number of data points in our data set. We've added an order n to our computation cost. So if you recall from the previous lecture that the complexity for linear regression, we're roughly going to be cubic in the number of features. Well, now we're going to be nm cubed. And that's a non-trivial amount of computational expense we've added. So like I said, leave one out cross-validation is really fantastic when you're working with a small data set, maybe thousands, at most tens of thousands of data points. But if you're talking about running a data set or running a model on millions of data sets and you have tens of thousands of features, it's going to get a little crazy trying to do this leave one out idea. So now, just to hammer home this idea of overfitting and generalization, here I'm showing a really nice plot. This is actually from the Hastie et al. Textbook, which summarizes the two problems we can have with our model, what we call kind of overfitting, and then sometimes what's called underfitting. So we've been talking a lot about overfitting, which is the case where we have an overly complex model. So what's happening here, this means that we have a model that has very low training error, but very high true or validation or test error. So what we're showing here in this plot is that, on this plot, is that on the left of the x-axis, these are simple models. So a really simple linear regression with no fancy features. Over here, we have really complex models. So the latest and greatest deep learning model with no regularization. And what's happening is that as we ramp up the model complexity, we're going to always get lower training error. Our training error is never going to go up from making our model overly complex unless we break our model, say by making it, adding a singularity or something. But as long as our model is just getting more complex in a reasonable way, we're always going to do better and better and better and better on training data. But on our held out test data, or during validation or held out validation set, what we're going to have is that as our model gets more complex, we're going to do better and better and better and better. And then at some point, we're going to hit an inflection point where our error on our test set is actually going to start going up and get worse and worse and worse and worse as our model gets more complicated. So the thing you want to do in machine learning is you want to hit this inflection point. And the only way to get a sense of this is by trying out models that get more and more complex and estimating your error on some validation set. And here I'm calling them an overly simple or an overly complex. And these are often called underfitting and overfitting, being the other terms here. So a final point that I just want to touch on, because it's actually something that a few people have asked me about in office hours, and it's an interesting point to raise as we've just discussed this idea of generalization and overfitting and underfitting, is that what is the difference between this view of the world in machine learning where we care about generalization, and how is this compared to traditional statistics? And in particular, this is a little brief aside for anybody who's interested in statistics or is taking maybe a statistics course on linear models. You might have found that the treatment of linear regression in this machine learning course is quite different from how these sorts of concepts are treated in a traditional statistics course. And the reason for this, pardon the typo, is that in traditional statistics, I mean, this is, maybe not all statisticians would agree with me, but the goal is that what we care about is estimating how does changes in some variable, some independent variable they're called, x, how does that impact our output variable y? So we care about fitting linear models in order to get an estimate of the parameters, of the coefficients, so we can know, oh, look, when we have a tumor that has a larger radius, that tumor is more likely to recur or not to recur. So really this goal of statistics is trying to use these models, use things like linear regression to help us understand how changes in one variable impact changes in another variable. And in statistics, traditional statistics, there's almost no mention of a train set or a test set or a validation set. Obviously, statisticians care about generalization, but these aren't concepts you're going to see as much. And instead, in statistics, there's a whole laundry list of techniques you use to make sure that your model is not violating particular assumptions. Now, we're not going to go into those in this course. They're very useful things to know, and I do not think that anybody, who wants to be, or anybody, I should say, who wants to be a serious machine learning researcher should probably take a statistics course, something like 324, or even one of the 598 courses in statistics. But the important thing is that in machine learning, obviously we still care about how one variable impacts another, but really, at the end of the day, all we care about in machine learning is how well can we generalize to unseen data. How well can we predict y from x and generalize and do well on data we've never seen before. So all of the tricks, all of the tools we're going to develop, they're all going to be with this goal, and it's going to be a very kind of pragmatic thing. What you're going to do as a machine learning researcher for the most part is you're going to look at your validation accuracy, make changes to your model, use intuition, and go and kind of iterate on that. And of course, it's useful to consider a lot of the statistical background for what sorts of assumptions you can make on linear regression and if your data actually holds for those assumptions. But in machine learning, we don't talk about that in detail in this course because we're focusing on this challenge of generalization, and our biggest litmus test is always our validation set, or at the end of the day, the test set. So any questions on that? Yeah. Oh, okay. Yeah. Adding, sorry? So the question was, is there any relationship between this idea of leave one out cross-validation and this idea that I talked about earlier where when we're encoding categorical variables, we can, the right idea is that instead of encoding every kind of possible value for some categorical variable as its own binary one, we want to do this idea where we actually only encode all of them minus one. This example with the blue and yellow categorical variable. So in this case, there actually isn't too much of a relationship there. So the idea with leave one out, and I think the important distinction is that the leave one out idea, this is happening on the data level with all the features. So we're not leaving out one of the features, we're leaving out one of the data points. So we're looking at, we have n data points, so we have 100 different examples of tumors, which have the features about these tumors, and trying to predict their recurrence time. For leave one out, what we're doing is we're doing 99 or 100 times training on 99 and testing on 1. But we're not fiddling with the individual features that we're using. All the leave one out is changing is what are the data points we're training on. Whereas this idea of variable encoding, this was happening kind of on the columns, where this meant that we're adding or subtracting different features. This is an important thing to kind of keep in mind, is that throughout this lecture, there's been modifications we're making to the columns of our data matrix. We're adding and taking away features, and also things we're doing with the rows of our data set. We're making train, test, and validation splits. Another question down here? Yeah. Hmm. Yep. Yeah, this is a great question. So the question was, I talked about in the beginning of this lecture of this idea that we can have a model that totally fails because we have variables that are perfectly correlated with each other. So this case here. So we can have, cases where we have different columns in our data matrix that are perfectly predicted from one another, and this can make our model totally break down. And generally, even if they're not perfectly correlated, this can be problematic. This can impact kind of how well the model trains. It just makes things unstable, etc. So we generally don't want variables that are very redundant or correlated with each other. And the question is, how does this relate, to in statistics? There's a lot of consideration of this problem and many techniques to detect and alleviate it. So in statistics, people often call this collinearity is the term. So it's called collinearity because it means, so in this case, the variable xm here is perfectly collinear with the variable xm minus 1 because we can perfectly predict xm from xm minus 1. And so in statistics, there's things called like the variance inflation factor, a variety of tools and diagnostics you can use to figure out which variables are highly collinear with each other. And the question is, how can we actually make use of these, say in machine learning, or kind of how do they relate to the concepts I've talked about? I think the short answer is that they are very useful things to use. So a very useful way to, to decide which feature to drop is by running these tests from statistics. And we'll go over actually some of these in a later lecture. So yes, it's very reasonable to actually use these tools from statistics in order to detect which variables to remove. But on the flip side, at the end of the day, what's going to be kind of the proof of which features you really should use, because statisticians don't agree, and machine learning people also don't agree about what the right tools are for removing or adding new variables. At the end of the day, what's going to be the answer in machine learning is your cross-validation performance. So that's kind of a little bit of the difference, whereas in more traditional statistics, there's going to be maybe in some sense some more theoretical reasons why one might be the right one or another depending on the assumptions you're making. Whereas here, we're maybe being a bit more pragmatic, and we just care about the performance on validation. Yeah. Yeah. Yes. Yes, definitely. So the question was, in statistics, it's quite often to use techniques, in particular a very famous technique called the bootstrap, where you kind of subsample, you take your original data set and you kind of increase the size of it conceptually by kind of sampling from it a bunch of times and running your model over and over. It's a very informal definition of the bootstrap. We'll actually talk about it formally later in the course. And the question is, how does this relate to, in particular, these ideas like cross-validation and leave one out cross-validation? It's very closely related. So, in fact, there is variations of cross-validation that are actually more conceptually similar to the bootstrap, and the main difference has to do with here we're doing this simple style, say for leave one out cross-validation, where it's leaving one data point out every time. In the bootstrap, there's this minor difference where you're actually resampling from your data, so you actually might double some data points. So you're just like uniformly sampling from your data set to build something to get an estimate of your error on. The reason for the bootstrap being a useful thing is that you can actually prove stuff about it. And we're not going to go into detail into a lot of proofs in this course, but we'll hopefully get to mention a little bit of that. So this is very closely related, these cross-validation techniques, to the bootstrap. Again, it falls a bit more on the pragmatic side, whereas later on when we do bring up the bootstrap idea, we'll talk about actually some of the formal guarantees that can give you. Any final questions? Cool. So with that, just going to give a quick recap. Ooh. Whoa. Yes. So to recap, I mean, I think at this point I don't need to go over it in detail again. It's important to have a train set, a validation set, and a test set. You will be asked to do this in Mini Project 1, and even if I'm not asking you to, you should always do it. Now, in terms of what are things you should take away from today, importantly, we learned a little bit more about linear regression, but more important than that, we learned how linear regression can fail. We didn't talk about gradient descent as much, but you should know that right now. This is going to be very important for the mini project. I'm going to ask you to implement linear regression or gradient descent for linear regression. So for those of you who are thinking, how can I get ahead in the course? I would say that implementing gradient descent for linear regression is definitely something you can do using Python, using NumPy, and really important, this notion of generalization. And just a quick heads-up reminder that there is a tutorial tonight in this room from 6 to 8 p.m. It's going to cover Python basics. If you never used Python before, highly recommend you come. And yes, otherwise, I'll be here for a couple minutes if there's any last questions.
I have a question regarding k-fold cross validation. So I seen something similar in